Okay, in this video we'll be tackling the last lesson of this chapter, which is solving polynomial inequalities. Okay, so this one feels like it's entirely new, but we're going to try to really relate solving a polynomial equation with a polynomial inequality, because that's going to help a lot. Okay, so what I have here, this is an inequality. So how do I know this is an inequality as opposed to an equation? Well, quite simply, there's a greater than symbol here as opposed to an equal sign. So if we replace the equal sign, so you still have a left side and right side, if you replace the equal sign with a greater than symbol, greater than or equal to, less than or equal to, those, if you replace that, then you will go from an equation to an inequality. So the idea here is that you're no longer looking for when the left side is equal to the right side. Okay, it's a big shift in your approach to the question. Now you're looking for, in this example, you're looking for when this cubic, when is this greater than 0? Okay, so we're not going to start with a cubic first. We're actually going to start with linear, okay, because I think a linear inequality is much easier than a cubic inequality. Now before I solve a linear inequality, I just want to go through some relationships, some rules with solving inequalities. So I'm going to talk about the 4 basic operations. So the 4 basic operations is adding, subtracting, multiplying, dividing. Okay, so I'm going to start with the number line. So what you see here is the fact that A is less than B. Okay, so clearly A is less than B. Now what if I chose to add by 2 to both sides of this inequality? Okay, so it'll be A plus 2 and B plus 2. Will this inequality symbol still hold true? Okay, if I take A and add by 2 and B and add by 2, will the sums, let's say, will the sum of A plus 2 still be less than the sum of B plus 2? And hopefully you can see in the number line, if I shift them both, if I move both 2 units to the right, the left side will still be less. The left side will still be less than that of the right side. And if you subtract both sides by some value, this inequality is still true. What if I multiply both sides by 6, by some positive number? Well, the left side will still be less than that of the right side. Now, I want to do something that will, I don't want to spoil it, but it's going to change things up a little. So let's say I multiplied both sides by -1. So now I'll have negative A on the left side and negative B on the right side. So I'm going to try to make it as symmetrical as possible. Okay. Hey, so now you basically created a mirror image, right? You reflected along about 0. So now negative A, negative B, what did you notice? A is less than B, but negative A is greater than that of negative B. Okay, so that is the one big difference with solving equations versus inequalities. Okay, so when you multiply or divide both sides by a negative value, you have to reverse the inequality sign, because of what used to be lesser is now greater. Okay, so you can really just stare at this number line and try to understand that, but that's the one key difference with solving equations and solving inequalities. Aside from that, everything else is fine. You can add to both sides, subtract to both sides, and when you multiply and divide by positive numbers, nothing interesting happens. Okay, what's lesser is still lesser. What's greater is still greater. Okay. Okay, so now I think we're ready to solve some inequalities. So let's look at this inequality. X minus 1 is greater than or equal to 3. X minus 1 is greater than or equal to 3. So just like with an equation, you can solve an equation graphically. Okay, like if I ask you when is x minus 1 equal to 3, you can solve for that graphically. So when is x minus 1 greater than or equal to 3? So this is f of x equals x minus 1. Okay, when is f of x greater than or equal to 3? So hopefully you realize that f of x is greater than or equal to 3 when x is greater than or equal to 4, right? From here, if you keep going, x is greater than or equal to 4. So I already know that this is true when x is greater than or equal to 4 based on the graph, okay? But I'll solve it algebraically because that's what they asked for anyways. Oh, sorry, they didn't specify. So anyways, add both sides by 1, so x is greater than or equal to 4. Hey, that's exactly what we saw graphically, all right? So I just want to add the fact that you can solve inequalities graphically, all right? So x minus 1 is greater than or equal to 3, and this inequality is true when x is greater than or equal to 4. So this is a big difference when we solve the equations, okay? You're not looking for when it's equal to 3, when is it greater than or equal to 3? Okay, when is negative 4 minus 2x less than 12? So this time I don't have a graph to help me solve this inequality. No problem. I'm just going to rearrange and isolate for x, and I can tell you when this inequality is true. So I'm going to add 4 to both sides, and then divide both sides by negative 2. But be careful, when you divide both sides by negative 2, you have to reverse the inequality sign based on what we said beforehand. So negative 4 minus 2x is less than 12 when x is greater than or equal to negative 8. Okay, so the good news is that we can solve inequalities. The bad news is that I'm very unlikely to give you linear inequalities. Okay, that's not the big focus of this chapter. I'm sure where we're heading. You know where we're heading. Okay, so the next sheet is a beautiful sheet to relate what you did in the previous unit to this unit. Okay, so in the previous unit, you were given a graph. Okay, you graphed a polynomial function, and then it was very likely that we ask you when is the function greater than 0 and when is the function less than 0. Well, if you think about it, is that not the same as solving an inequality, right? I ask you, when is the function greater than 0? That's an inequality right there. So in a sense, you can really say we were solving inequalities in the previous chapter. Okay, we just didn't use the word inequality. So I gave you the graph of the polynomial p of x. When is it greater than 0? So it's greater than 0 when x is anywhere from here to here, or when x is greater, or when x is from here to here onwards. They're arrows, of course. So determine the solution. P of x is greater than 0 when x is, let's see, negative 3 to 1. I'm not including negative 3 and 1 because at negative 3 and 1, it's equal to 0. It's not when p of x is greater than or equal to 0, just when it's greater than 0. Or when it's greater than 4. Okay, beautiful. All right, let's do one more. When is p of x less than or equal to 0? Let's see. P of x is less than or equal to 0 when x, oops, it's a round, should be a round bracket. It's less than or equal to 0, so it's negative infinity. Negative 4 or negative 2 to 3. Let's put some square brackets here. Okay, there we go. So when you were trying to solve the two inequalities, did you notice how the x-intercepts of the graph helped you find the solutions? We're going to answer the question in the next page, but hopefully you can agree that the x-intercepts the x-intercepts created, and we said this in the previous chapter too, created intervals. Okay? They created intervals where the function is positive and where the function is negative. So I can easily answer when p of x is less than or equal to 0 just by looking at where my x-intercepts are, because that's creating intervals for me. Those are creating intervals for me. Okay? So, we're slowly working up there. Therefore, we can solve any polynomial inequality using the zeros of the related polynomial function because it divides a function into intervals that can be used to solve the inequality. So basically, that's actually what I wanted you to write on the previous page. But that's essentially what I said, right? Okay, so now let's solve another inequality. But this time, this is a quadratic inequality. So first, we want to identify the zeros, which will then enable us to build the interval table. So first I'm going to say let f of x equal x plus 3 times 2x 3. So that means our zeros are negative 3 and 3 over 2. And the orders are 1. If I don't specify the order, it's implied to be an order of 1. Now the next thing I'm going to do is I'm going to build the interval table. Okay, wait a minute. This is exactly what we did in the first chapter. So I don't know if you remember, we were learning how to graph polynomial functions from factored form. And to find out whether the function positive or negative over that interval, we created an interval table and we used test values. So guess what? You're doing the exact same thing. Okay, use a test value, use a test value, use a test value. So like 0 would be a great test value. And you realize it's equal to some negative number, negative 9. Use some number greater than 3 over 2, I don't know, use 2 for example, and you realize that it's positive. So now I know exactly when this quadratic is greater than 0. When x is less than negative 3, right? That's what my interval table said. And when x is or when x is greater than 3 over 2. That's what my interval table said, right? So very reminiscent of what we did in the first chapter. Okay, really try to relate the two because it's honestly the same thing. Okay, could we have determined the answer without creating a table? Absolutely. Graph the polynomial. Right? If you graph the polynomial, then you have what we had on the previous page. Okay? You graph it and then use the x-intercepts to create intervals and then stare at it and find out where it's above the x-axis or where it's below the x-axis or where it's on the x-axis, where it's above or on the x-axis, so forth and so on. Okay? So a graph is very powerful because it can help us solve this inequality. Okay, so to solve a polynomial inequality algebraically, okay, first you have to set it equal to 0. All right, set it equal to 0, and then determine the zeros of f of x, because the zeros of f of x will help you create the interval table, and then you can fill in the interval table, and once you fill it in, you can solve the polynomial, solve the inequality. All right. So, let's solve this inequality. How do we want to do this one? Let f of x equals x plus 4, x minus 2, x plus 1. Okay, how do we want to do this? So we can solve it algebraically or graphically. Now, they didn't specify, they just said solve. So if they say solve algebraically, I have to do it algebraically. And I'll show you the different algebraic techniques, but you know what? I just want to show you how beautiful solving by graphing is. 3 to 1, cross, cross, cross. Okay, these are skill sets that you gained in the previous chapter. Now I can graph it. I can tell you exactly when it's less than or equal to 0. Therefore, f of x is less than or equal to 0 when x is less than or equal to -4, or from -1 to 2. Bam, beautiful. Okay, so I personally, if they don't specify, I will always solve the inequality graphically. There's another way I lean towards too, but this, I would argue, this is my second most favorite technique of solving an inequality. So I'm going to solve example 4 different ways. Okay, so you tell yourself, or you tell yourself which one you prefer. But no matter which technique I choose to solve this inequality, I have to factor. Okay, so this brings us back to the emphasis of the unit. If you cannot factor, you cannot do, I would argue, 80 to 90% of the questions on this test. So definitely factor. Okay, so let f of x equal to x cubed plus 9x squared plus 26x plus 24. All right, play the guessing game because I can't factor by grouping. 1 second, let's see. What's a good guess? -2 is a good guess. So since x plus 2 is a factor, by inspection, this must be x squared, this must be 12. So this middle term 2, but I want to make a 9, so it's a 7. Alright. If you're still using synthetic or long division, I really recommend this technique. It's a game changer. It's really worthwhile learning. All right, so let's do 4 different ways. Okay, so but regardless of which of the 4 ways you choose to use, you have to factor. Okay, that's unavoidable. All right, so the first technique is the graph. Okay, oops, I forgot the label in example 3. Y equals f of x. All right, so first technique is the graph. Solve by graphing. But if this specifies solve algebraically, I cannot do this, okay? So -2, -3, -4, quadrant 3 to 1, bam, bam, bam. Okay, so that's technique number 1. Technique number 2 is to solve by using an interval table. So you can say intervals here. By the way, the textbook has a different interval table. It's a little more cumbersome, but it's up to you if you want to do it that way. And so some teachers and some textbooks, they like to express every single factor. So x plus 2, x plus 3, x plus 4, and then finding out the sign of each factor. They then find the sign of the product. I personally just find the sign of the product. Okay, so the first interval is -infinity, -4, -4, -3, -3 to -2, -2 to 1, and 1 onwards. Ooh, okay, so I actually don't use test values. I just really graph it in my head. I know that it's quadrant 3 to quadrant 1, and the signs alternate because all the zeros have an order of 1. So it's just bam, bam, bam. I always make a physics joke here, but I don't know if people online will get it. But I think of a battery. Ha ha ha. Okay. So that's my second technique. My third technique is actually really similar to the second technique. So what I do is, instead of creating the intervals in the form of an interval table, I draw a number line and I demonstrate the intervals. Okay. So I create the intervals on a number line, and then I basically still find the sign of f of x. So put negative, positive, negative, positive. Oops, I forgot. I don't know why. Why did I add a 1 there? I'm so sorry. I have no idea where 1 came from. Yeah, and it would make no sense to end off in a negative because it's quadrant 3 to 1. That was silly. Okay, so negative, positive, negative, positive. You don't have to follow the exact form. You could put the negative at the top, but I feel that students like to see the location of the plus and the minus to emphasize the relationship with the graph. But you know what? I actually prefer this way the most. This is to me the fastest way to go about it. But it's really reiteration. It's another way of showing the information presented in the interval table. So these are zeros at -3, -2, and -4, and at those intervals I can tell you whether the function is positive or negative. Okay, so I got 3 ways so far. The 4th way is my least favorite way. Okay, this one is called cases. So this is also an algebraic technique. So I don't like it because it takes a lot of time, and it doesn't work very well when you have more factors. So if you have 4 factors, this would be a horrible technique. So even if I have 3 factors, it's a horrible technique. So it's very easy to miss solutions. So how do you solve by cases? What you have to do is basically try to come up with scenarios where the inequality is satisfied. So when is the product of these 3 factors greater than or equal to 0? So case 1, when all 3 factors are positive, right? When all 3 factors are greater than or equal to 0. So what you do is you ask yourself, when is the first factor, second factor, and third factor simultaneously positive? Okay, so you solve each individual inequality. And then you ask yourself, when are all 3 inequalities satisfied simultaneously? So when x is greater than -2, x is greater than -3, x is greater than -4. So you will say x is greater than -2. Okay, that solves case 1. Okay, why is it only how many cases are there? Well, how else can you make a positive value here? Well, case 2 is when x plus 2 is positive, but x plus 3 is less than or 0, x plus 4 is less than or equal to 0, right? Because positive times negative will also give you positive. So just as a side note, case 3 would be, let's say, negative, negative, positive, and then case 4 would be negative, positive, negative. All right, and that would be all the different ways to create a positive value by multiplying 3 numbers. And that's why I said if there are 4 factors, you can easily miss a case, and that would be catastrophic. Okay, so anyways, let's solve case 2. So x is greater than -2, -3, x is less than, there we go. Okay, let me just triple check. Yep, okay, so x is greater than or equal to -2, less than or equal to -3. Well, this is not good. Because if you're greater than or equal to -2, less than or equal to -3, how is that possible? So there's no values of x which simultaneously solves all 3 of these inequalities. So therefore, case 2 gives us no solutions. How about case 3? So what did I say? Case 3, we're going to make the first and third factor negative. X plus 2 is less than or equal to 0. X plus 4 is less than or equal to 0, but x plus 3 will be greater than or equal to 0. Okay, let's try it now. X is less than or equal to negative 2, x is greater than or equal to negative 3, x is less than or equal to negative 4. So when do we solve case 3? Let's take a look. Less than or equal to negative 2, greater than or equal to negative 3, less than or equal to negative 4. 1 second here. X is greater than or equal to negative 3, less than or equal to negative 4. Okay, really picture that. How is it possible that you're greater than or equal to negative 3 and also less than or equal to negative 4? Therefore, since I can't simultaneously solve these two inequalities, no solutions. Alright, we'll do one last case. Okay, case 4. So case 4 is when, 1 second, first, second, and third is negative. First and second you want to be negative now. X plus 2 is less than or equal to 0. X plus 3 is less than or equal to 0. X plus 4 is greater than or equal to 0. Okay. So x is less than or equal to negative 2. X is less than or equal to negative 3. X is greater than or equal to negative 4. Alright, so let's see. Okay, when is this satisfied? When it's less than negative 2. Less than or equal to negative 2, less than or equal to negative 3. So less than or equal to negative 3. Okay, beautiful. So this, you can actually solve all three inequalities when you're between negative 4 and negative 3. Okay? If you investigate, these three inequalities can be solved simultaneously when x is between negative 4 or any value from negative 4 to negative 3. I should have stayed consistent. I should have chose interval notation on both sides. Let me fix it. So x is greater than or equal to negative 2, so it's... Okay, so you can solve graphically. You can solve using an interval table. You can solve using a modified interval table in the form of a number line. You can solve using cases. All right, so lots of different ways to solve it. But at the end of the day, what's the first thing you do? Factor, factor, factor. Okay, so you know what? We should really do a therefore statement and say what's the answer. Therefore, f of x is greater than or equal to 0 when, so no matter which method you use, you get the same answer. And x is from negative 4 to negative 3, or when it's greater than negative 2. Okay, so you would come to the same conclusion with any of the four methods that we tried.